Dear students, before the lockdown, we have studied the principle of NMR, that is nuclear magnetic resonance, and also obtained the Bloch equation and its solutions. So, where we have drawn the graph, that is, as you know, the susceptibility is chi dash and chi double dash. Here chi dash is the real part of the complex susceptibility chi, and chi double dash is the imaginary part. This is what you have studied. That is, the actual susceptibility is the sum of real part and imaginary part. Then after Bloch theory, you have plotted the graph connecting chi dash versus omega naught minus omega. This is the shape of the graph you have obtained. Then you have plotted the graph chi double dash versus omega naught minus omega into tau 2. You are getting the graph of this kind. Right. That means chi double dash indicates the absorption of energy from the incident electromagnetic radiation. So that means the absorption of energy is maximum when the Larmor frequency is equal to applied frequency. This is what we have studied earlier. In this video lecture, I will show you chi double dash represent the absorption of energy from the incident radiation. So, the rate of absorption of energy per unit volume per unit second can be shown as P is equal to minus omega divided by 2 pi integration over a complete cycle, that is 0 to 2 pi into m into dH. Here negative sign indicates that energy is absorbed by the system. Now, as in the Bloch theory, we have defined m of t is equal to chi dash into 2h1 cos omega t plus chi double dash into 2h1 sin omega t. This is the equation I am taking from Bloch theory. And also the magnetic field is equal to 2h1 cos omega t. So now what we have to do is we have to substitute the value for m and dH in this equation. If h is equal to 2h1 cos omega t, then you can write dH is equal to 2h1 d of cos omega t. So therefore, rate of absorption of energy P is equal to minus omega divided by 2 pi integral, substitute the value chi dash into 2h1 cos omega t plus chi double dash into 2h1 sin omega t into dH. So, dH is equal to 2h1 d of cos omega t. So, therefore, this is equal to, here you can observe 2h1 is common. Take outside the bracket. Then it becomes 2h1 whole square minus omega divided by 2 pi into 2h1 whole square integral chi dash into cos omega t plus chi double dash into sin omega t into d of cos omega t is nothing but minus sin omega t d omega t. Sin omega t d omega t, I am writing here, minus into minus plus. So now this is equal to omega divided by 2 pi 2h1 whole square integral now into chi dash into cos omega t into sin omega t plus chi double dash into sin square omega t into d omega t. Now you have to integrate this. Then here this is equal to omega by 2 pi 2h1 whole square integral chi dash into, this is cos omega t, sin omega t is nothing but sin 2 omega t divided by 2 into d omega t plus chi double dash into 1 minus cos square omega t divided by 2, 1 minus cos 2 omega t by 2 into d omega t. So now here this is equal to omega by 2 pi into 2h1 whole square integration. Here it is now chi dash by 2, this is cos 2 omega t, limit from 0 to 2 pi plus here chi double dash by 2 into, this is omega t minus sin 2 omega t divided by 2. Here also limit from 0 to 2 pi. So now you put the limit here. So then what happens? P is equal to omega divided by 2 pi into 2h1 whole square. This becomes cos 2 pi minus cos 0, 1 minus 1 0. First term reduces to 0. Here in the second, sin 2 omega t, sin 2 into 2 pi minus sin 0, 0 minus 0, 0 only. Remaining term is chi double dash divided by 2. Upper limit is 2 pi. So what you are observing now? So just cancel the terms. So that is equal to omega divided by 2 pi into 2h1 whole square chi double dash by 2 into 2 pi. So 2 pi get cancelled. So therefore this is equal to omega divided by 2 into 2h1 whole square into chi double dash. That means you can observe P is proportional to chi double dash. That means rate of absorption of energy per unit volume per unit second. That is directly proportional to chi double dash. Therefore, chi double dash indicates the rate of absorption of energy. Then it can be shown that at resonance, the maximum absorption of energy is equal to omega into omega naught into chi naught into h1 square into tau 2 divided by 1 plus gamma square h1 square tau 1 tau 2. Here chi naught is the susceptibility at resonance, tau 2 is the spin relaxation time. So this is the expression, but under the condition that if gamma square into h1 square into tau 1 tau 2 is much less than 1, then this becomes approximately omega into omega naught chi naught h1 square into tau 2. Next, we will discuss about line shapes and widths. That means, here when you are considering to the absorption curve chi double dash versus omega naught minus omega into tau 2 graph you are getting. So, what is the shape of the graph? Whether this resonance curve is sharp or whether the resonance curve is Gaussian or whether it is flat, what contributes to the shape of the resonance curve, that one we have to discuss under line shapes and widths. The line width of all materials are not same, being generally much less for liquids and gases than for solids. That means what? When you are considering the absorption curve for gases and liquids, if you compare, say for example you are comparing the graph of a particular gas with a particular solid, then the curve is sharp for gases and it is flat for solids. So, for some liquids, the line widths can be narrow so when you consider the line width, so here when you calculate the line width, it is of about 0.5 CPS, cycles per second or hertz. For a particular solid, the value is of about 5000 CPS or 5000 hertz. Then you can observe that 5000 hertz means it is a flat curve. So, that means the difference clearly points that some phenomena occurs in liquids does not occur in the metals or solids. The phenomena is assumed to be rapid atomic diffusion. The two effects, namely nuclear spin-spin interaction and spin-lattice interaction, that broaden the width of resonance. As already we have discussed about spin-lattice relaxation and spin-spin relaxation. As you know, spin-spin relaxation that leads to the local field. So therefore, this local field affects the line shape and width of the resonance curve. See, if the nuclei move at the faster rate in case of liquids and gases, the magnetic moments of the neighboring nuclei, random as they are, average out to be 0 and the line is the narrow. That means, as you know, in gases, the molecules are moving randomly. Each molecule is considered to be a dipole moment. Therefore, if that gaseous molecules are moving at the faster rate, that molecule is not encountered by the local field produced by the other dipoles. Therefore, here what happens is, in comparison with solids, its line shape is sharp. See, the examination of the shape and the width of magnetic resonance curve yields much information concerning certain magnetic effect, namely the relaxation phenomena. See, in order to understand the shape of the magnetic absorption line, we are considering a function g of omega. Let us you consider a function g of omega, which is the function of frequency omega, which is we are considering in a fixed magnetic field H. See, let us you consider this is a normalized wave function. That means if you are writing integration 0 to infinity g of omega into d omega, then this is equal to 1. This condition is satisfied by the function we have selected in order to explain the line shapes and widths. So that is equal to 1. Okay. So now in order to understand the line shapes in liquids and gases, Lorentz proposed a model. According to Lorentz, each molecule or atom is considered to be an ensemble of harmonic oscillators. So they are considered as ensemble of harmonic oscillators. So these harmonic oscillators are randomly moving. See, gas molecules are randomly moving. When they are randomly moving, they are colliding with each other. So that collision is of a short duration. Collision of a short duration occurs when the molecules are moving. So as at each impact, Lorentz assumed that there were sudden change of phase. So that means what? When you are considering this is one dipole, this is another dipole. Okay. So when these two dipoles are colliding or harmonic oscillators are colliding, there is a sudden change of phase, say like this. Or if two are like this, when they are colliding with, what happens? They are changing their phase. See, this sudden change in the phase is takes place for a very short interval of time. Very immediately it will take its original phase. So this leads to the broadening of absorption line in case of gases and liquids. Say, why? Because when the phase undergo variation, in order to retain its original phase, it absorbs the energy from the applied electromagnetic radiation. So because of that, what happens? Instead of absorbing at a particular frequency, it absorbs some other frequency. Because of this, curve comes like this. So therefore, that is the reason for the broadening of line shape in case of gases and liquids. Then here, just like Bloch equation, Lorentz also deduced the expression for g of omega for liquids and gases as tau 2 divided by pi divided by 1 plus omega minus omega L whole square into tau 2 square. So here you can observe here the effect tau 2 spin lattice relaxation, spin relaxation time, omega L Larmor frequency, omega is the applied frequency. See, when omega is equal to omega L, what happens? g of omega. It's the maximum value you are getting. Because omega equal to omega L, this term reduces to 0. The expression becomes tau 2 divided by pi. So therefore, here just we have seen what is the reason for line broadening in case of gases and liquids. But same explanation, and also it can be shown that the half width, this half width delta omega is equal to 1 divided by tau. The same explanation does not hold good for solids, because in solids the atoms or the harmonic oscillators are fixed about its position. But in some materials we can observe the diffusion of atoms, but diffusion of atoms is not considered under this case. Now, by ignoring the atomic diffusion, let us see what is the reason for the broadening of line shapes. See, for solids, we can consider either nuclear or electronic moments. That is, each atom or molecule is considered to be an atomic dipole. Therefore, when you are considering these atomic dipoles are present, let us say n number of atomic dipoles, right? So now each dipole is just like a tiny magnet. So because of this, what happens? See, when you consider one dipole, it experiences the magnetic field from the remaining n minus 1 dipoles. That means here, see, magnetic field experienced by this is called the local field. See, local field, already we have discussed this one. Local field experienced by the dipole A is not equal to local field experienced by the dipole B. Different dipoles experiences different amount of local field. So because of this, what happens? Different dipoles will get resonated at different frequencies. Because of that, what happens? We are getting a broadened absorption curve. So that means the distribution is almost a Gaussian distribution we are observing. So omega minus omega L or omega naught you can consider tau. Right. Omega naught equal to omega L, that is nothing but Larmor frequency. Okay. So almost it is a Gaussian. So for solids, the normalized wave function g omega is equal to tau 2 divided by pi into e to the power exponential minus omega L whole square into tau 2 square divided by pi. So again, absorption resonance means omega is equal to omega L. Under this case, what happens? E to the power 0 is equal to 1. At omega is equal to omega L, we are getting g omega maximum. This is equal to tau 2 divided by pi. So similarly for solids, half line width delta omega can be shown as 1 divided by tau 2 into pi into log 2 whole to the power half. So this is what we are observing in case of solids. The mainly broadening is due to the effect of a local field, that is spin relaxation is responsible for the broadening of absorption lines. See, as you are considering here, local field means there are n number of dipoles. Now, it is the calculation of line shapes for such a system is the contribution of local field, the calculation of local field at the different dipoles. It is very difficult. So now it can be shown that nth nuclear moment is equal to magnetic moment omega minus omega L to the power n average, that is delta omega to the power n. It can be shown that integration minus infinity to plus infinity omega minus omega L whole square g omega d omega. So here it can be shown that it can be proved that for odd numbers, that is if n takes 1, 3, 5 etc, g of for odd n, g of omega is equal to 0. So that means only for even n the magnetic moment, that means you can consider the magnetic moment of second, fourth, sixth, likewise for odd dipoles we have to consider. So now using this concept, say for n is equal to 2, the value of omega minus omega L can be taken as delta omega whole square. Using quantum mechanical approach, we can show that this is equal to sigma omega square into normalization bracket notation. We are using n I, that is the nuclear spin, n dash whole square divided by sigma n whole square minus omega L square n dash summation. So using this we can show the local field is equal to delta H. This is the local field at the moment n is equal to 2. This is for single crystal. We can write this is equal to 3 by 2 into I plus 1 gn square into mu b n square divided by n summation I k into 3 cos square theta ik minus 1 divided by rik whole square. See here in this expression, this is the local field at the moment 2, magnetic moment at 2, okay, for n is equal to 2. Here n is the total number of nuclei that make important contribution to the local field at a nucleus, which is at a distance rik. So now you consider a particular nucleus. So that nucleus experiences the local field from the n number of nuclei. Now here when you are considering to Rik is the length of the vector from the nucleus I to k. That is, here you have to take the summation, right? Therefore, for you have to take a particular nuclei as reference, then remaining n nuclei you have, so it's a distance Rik. If you consider n is equal, I is equal to 1, k is equal to 0, then you can consider between 1 and 0 how much distance. If I is equal to 2, second one, right? Likewise, for all nuclei you have to take summation. Theta ik is the angle between the vector Rik, so that means it is the ith nucleus, this is the kth nucleus, so the distance is this. Theta ik is the angle between the applied magnetic field and this vector. So that is angle between Rik and the direction of the magnetic field is theta ik. From this expression you can observe that the local field is the function of distance between the ith nucleus and kth nucleus, and also it depends on the angular. So theta ik, it represents the angular. Therefore, angular dependence is also we have to consider for the contribution of the local field, which broadens the line shape. Thank you.